This is blocks analysis. We are back in the textbook chapter. We're going to start back up from chapter 3. Last time I think we went to the end of chapter 2. I think it was 2.8.6. I'll briefly explain my thought process on 2.8.7 and 2.8.8, and then I wrote a couple of other solutions while not posting them on YouTube, so maybe explain those quickly, the thought process. So for 2.8.7, it's saying that if you have two decimal sequences of infinite length and they're equal, and there's no repeating decimals with p minus 1, if you're in base p, then each single term of these decimal sequences must be equal. I think this one you have to use, maybe you don't have to, but it's very advantageous for you to use some of the previous proofs, especially here, like a 2.8.5 part 4. I think that one was very useful. Let's see, where is that? Yeah, so essentially I think you want to show that, if there is a different term at any point in the infinite sequence, identify the first point where they diverge from each other, and then show that the one which has a smaller term at the point of divergence will never be able to catch up to the one that has a bigger term. And the way you do that is by using this lemma 2.8.5 part 4. And so yeah, that's basically essentially the meat of the proof, the core structure of the proof. You can pretty much immediately go in here and say that this lower term E, the lower sequence E, will not be able to catch up to the sequence AI, and you plug this one in. That's kind of the idea. So let's see, for 2.8.8, yeah, this is basically asking for the division algorithm except for integers. It's a bunch of flipping signs around, and you may imagine this in like a more coordinate, like geometric way as well. Like, for example, it's easier to imagine like if you have two negative numbers, it's almost like if you have two positive numbers. So except that the remainder will be of a negative sign, but then you can just add one more of the quotient to make that a positive remainder. So that's essentially the idea, and you do this for a couple of other things. So for example, if you have 7 and 3, your remainder is 1. You have -7 and -3, your remainder is -1. But you can just add another 3 to make it 2. So for example, -7 is -3 times -3 plus, that's the wrong, wait, actually, sorry, -7 is 3 times -3 plus 2. So yeah, there's a way that you can always sort of find a nice remainder. So that's kind of the proof for that. Yeah, and 2.8.9, I think I might have neglected to do this question actually. The integers, even if there's some k such that it's n equals 2k, it's odd if there's some k such that n equals 2k plus 1. Prove every integer is either even or odd, but not both. So I think the best way to do this is to just assume that it's both, and then you have, well, actually, since I didn't do this question, I think it wouldn't hurt for me to quickly type it out. It doesn't seem like it would be a very difficult question to do quickly. So let me see the question again. So it's asking about integers. Okay, so okay. So previously we already had the division algorithm, so we can use that immediately. So for any integer which is, oh, let me move the microphone a little bit. Okay, so this is immediately follows from the previous exercise, and you can pretty much tell that there's only two options. There's only two options for R. So then it pretty much makes sense that it has to be either even or odd. And I think, I'm not sure if the division algorithm says uniqueness. Yeah, it says uniqueness. So since it's unique pair of QR, then R must only be 0 or 1. It cannot be both. But we can also do another proof for it. It shouldn't be too difficult. I think maybe there's no need. Just use the previous thing we proved already. This one is pretty straightforward. So we can discuss some of the next exercises in section 3.2, the limit of functions. This one feels like a pretty standard analysis, like introduction. Not that I know much about standard analysis introductions, but you know, it looks pretty normal. Nothing excessively crazy here. So we can briefly go over some of the lemmas and theorems for, I think, for my benefit. Could be nice to have a reviewer, to have a review. So one of the specific parts that this specifies is I has to be an open interval. And then it specifically only defines f on the I minus c. So you can have the notion of a limit existing where the function isn't defined, and L is unique. Yeah, so we're saying that the limit must be unique. And it gives a proof that if you have two limits, then you cannot be infinitely close to both if they're different. And that pretty much makes a lot of sense, and it uses some trick with the triangle inequality to demonstrate that. Yeah, but maybe more interesting is the part about the open interval why is it necessary to have this open interval? I think it's because then for any point inside the open interval, there always exists a neighborhood around this point which is in the open interval, which is where you can do this sort of analysis epsilon delta stuff. Otherwise, if you have a point inside the interval but it doesn't have any open neighborhoods that are entirely contained in the interval, you might have some trouble. Of course, for like 2D, you can do a one-sided limit, but maybe that's not universally the case for some other things. Like if you are not working with real analysis in one dimension, you could maybe encounter more complicated situations. Okay, so theorem 3.2.4, let it be an open interval and let this be a function. Suppose the limit exists and there is some bound. Oh, I guess if it's above 0, if the limit is above 0, then somewhere around it, it has to be above m. And same with the opposite. This intuitively does make sense because you have to approach this limit at some point. And one of the most intuitive places where you can think is maybe you're like half of the limit or something. Because half of a positive number is another positive number, so and the distance between that and half of itself is easier to define. Lemma 3.2.7, if this exists, there's some delta such that the restriction of f to this is bounded. Okay, yeah, I mean this is also making some good sense because like if you get close enough to this, let's say within certain delta like this, then you must also be within epsilon of the limit. And then let's say that limit has some defined value like L, then you'll be like plus minus epsilon within this, which means you'll be bounded too. But you might need to do some absolute value gimmicks, like this sort of triangle inequality absolute value gimmicks, but intuitively it makes sense. Yeah, again, this says that if the limit as it approaches f is 0 and that g is bounded, then it's 0. This makes sense. Because this value can never escape a certain value, but this will get infinitely close to 0 as you approach it. So you just want to restrict the neighborhood for this f enough so that it can bring this down to within an arbitrarily close enough to 0. So I think that's in fact what they are doing here, is that for any epsilon, as there's some sort of value bound for gx, then you just want to bring fx close enough such that it's close enough to the limit point such that it will cancel out that m. Let's see, there's a couple of definitions here concerning like the addition, subtraction, multiplication, and division of limits. Nothing too out of the ordinary, and there's a scalar. Yeah, this one may be a little bit more unusual. I think maybe we will encounter this. Oh, it's not even limits, it's just function operations. Yeah, and here is the limit. Yeah, this is pretty straightforward, I think. The only caveat is maybe with the division, like you have to make sure the limit doesn't approach 0. Yeah, and this one, it kind of looks like a mini squeeze theorem. Yeah, see, now it kind of expands on that to a full squeeze theorem. Yeah, so what is it saying? If those limits both exist and this is true, f is less than g on everything in the interval, then the limit of f must be less than the limit of g. at any point inside the interval, or I guess at C specifically in the interval. Yeah, I mean, it's not immediately clear how to prove this. I think one way you can go about it is if the limit is actually greater, then you can find some like epsilon over 2, where some value of f must be like close to this enough so that it's greater. Sorry, what am I saying? Oh, gosh darn it. Okay, so if the limit of f is greater than the limit of g, there must exist some value of g and f such that g is within epsilon. Let's say the difference between the two is then epsilon, and there's some g, there's some x naught where g of x naught is within epsilon over 2 of gx, and some, well, actually you probably use like 2 different epsilons and 2 deltas, and then find the lesser of the 2 deltas, and then, or actually you use the same epsilon, use epsilon over 2, then you find the lesser of the 2 deltas, and you say any x naught within that delta of C must mean that x naught is closer to this g of C, the limit, or something. Okay, I'll do a proof for this later, but because it's an exercise anyways. I think I know how to do this, and this is just this applied on both sides, so I think nothing too crazy. Is it? No, that's not true. I mean, the second half of the conclusion is obviously different. Yeah, this one we'll see later actually. But what is it saying? So yeah, it's a squeeze theorem. Yeah, I think you can go by proof by contradiction. Let's say g of x is less than L, then that cannot be true, because you have theorem 3.2.13 that will contradict that. And if you say g of x, the limit is greater than L, that also won't be true. And since this is a part of the real number, since not greater or less than L, then it must be equal to L by some of the axiom about real numbers and their inequalities or signs. Not signs, just inequalities. Like there's an axiom saying that it must be less or equal or greater than some other number. So yeah, I think you could do that. I think they didn't do that here. I think they probably went with something else. Okay, so they're trapping the gx within the plus minus epsilon neighborhood of L for arbitrary epsilon. So that means g of x must in fact be L, since there was a small lemma showing this earlier or something like that. Or I think they didn't even need to do that. They just straight up used the actual limit definition. Yeah, and they used the lesser of the 2 neighborhoods. Okay, I see. Why is it I feel like I didn't actually read this part of the section? Oh. Okay, see, now they remove the requirement on the open interval, because to accommodate the one-sided interval, you need to remove that requirement. Well, I mean, I guess you don't need to. You can still have a one-sided limit inside of an open interval, but it won't be as meaningful because you can have a two-sided interval then. Yeah, so I guess they are doing the same definition except just with plus epsilon not minus, or plus delta not minus delta. In the same situation here. yeah, there's nothing too crazy there. Then this function exists if the limit from both sides exists, if and only if. Yeah, I think this is a straightforward. It follows from the definition of this. If you piece these two inequalities together, you will get x minus c absolute value is less than delta. So the fact that it's an if and only if makes sense too. So I think that's that. Nothing too crazy there. Yeah, I think this is pretty normal stuff. Nothing too crazy. Yeah, so 3.2.1 proof that the limit is equal to mc plus b. So standard technique, you use fx minus fc and try and make that somehow related to x minus c. And in this case, the relation is by multiplying by m, or the absolute value of m. Oh, I think I have made a mistake here. I accidentally typed some extra characters here. Don't need those 2 characters. Yeah, so that's straightforward. For the next one, yeah, again, the technique is to subtract it. So I didn't show the scratch work. Usually for scratch work, you will go backwards and do this first, do the subtraction first, and relate this expression to the difference between x and c and some other related variable, and turning it into a constant so you can actually use it directly in your epsilon delta relation or function or mapping. I guess like one other thing you may consider for this is this is sort of assigned for maybe I want to say uniform continuity, where you can relate those two by multiplication by a constant. If you can relate epsilon and delta. If you relate them by some variable term which changes according to where your c is, then that's a sign, or maybe your x or your c is the center of your limit is, then that's a sign of non-uniform continuity or just normal continuity. You have this. Yeah, I think the trick is to notice that at every point within the every point that can be possibly be considered for the limit, the denominator is not 0. So again, I think it's crucial to grasp that x for any point that can be considered for the limit cannot be 3. So you don't need to worry about that. Yeah, so this is saying that these two statements are equivalent. Limit of x, limit of f at c is L, or limit of f minus L at c is 0. So I think for the forward direction, you can apply the definition of the limit and then lead to this. And then you can say, like, for the same epsilon, I choose the same delta. For the first function as the second function, I choose the same delta for both, and then it will work out. And it's the same the other way around, because the expressions when you evaluate them for delta is the same. Yeah, this one it can be a little bit tricky. I thought about it a little bit more on the bus. I think I spent a couple of solid minutes, if not 10 minutes even. I shouldn't have spent that long, but sometimes I'm not the best or even I'm not even the middling talent, so to spend more time in this. So you do have some limit which approaches 0, but some other limit which breaks this limit so much that it cannot balance it out and bring it to 0. That's kind of the idea. Uh, 3.2.5, this one is a restriction. Like, the forward direction is not too interesting, I think, because you're just applying the definition of what it means for x to be evaluated for f restricted to j. It's the same as normal f, I think, but the other way is more interesting. I have to remember why. I think there was a specific reason. I think it was because if you go the other way, so say you are within, so every neighborhood around, let me think about this. Because the definition of the limit is that it has to satisfy two requirements. One is that it has to be within the domain, like it has to be within this I minus c. The second one is it has to be within the delta neighborhood of your choice. But if a neighborhood in here is greater than what can be contained in the j, you just have to say then that x doesn't satisfy the requirement to be considered for the limit, so there's no need to consider that. But going the other way around, there may be some neighborhoods in this which might have like some values that are also outside of j in this f that need to be considered. In that case, it's a bit trickier.